showing up. We wanted to do this talk as kind of a celebration for the Nobel Prize in Chemistry, which was awarded yesterday. And the Nobel Prize was started in 1901, because chemists were always kind of excited to see who wins it every year. And some of the people who won it have taken chemistry classes, so you'll recognize these names, like Arrhenius and Rutherford, Marie Curie, Grignard, okay, Nernst, Diels and Euler, and Pauling. So just a few of many. So a lot of people who win this award become really well known and end up in your textbooks. So the people who won it this year was jointly shared between Martin Karplus, Michael Levitt, and Aryeh Washell. Very bad pronouncement. And they won it for laying the foundations of computer models to help researchers understand and predict chemical processes. And it turns out that Dr. Galbraith, a lot of the stuff he does is based on a similar kind of idea. So I thought he would be a very good person to kind of explain some of the basic theory behind the work and why this work was worthy of winning the Nobel Prize. A little background of Dr. Galbraith. He got his BA in chemistry from Colorado College, his PhD from the University of Georgia, and did postdocs at the Hebrew University in Jerusalem and University of Washington. And then before coming to Marist, and his research is into the studies or computational studies of chemical bonding using valence bond. So,
all right, thank you, Neil. Yeah, like we said, yeah, we tried to put this together pretty quick. I know it's pretty last minute, but yeah, we wanted to get this while it's still a big news story and still of interest to a lot of people. Had it on their minds. A lot of people contacted me and said they couldn't come tonight because of previous plans. That's what happens when you schedule something a day in advance. But we're videotaping, so hopefully we can put this up on the Marist website or at least the chemistry Facebook page, so a lot of those people will be able to come see it on their own time. All right, so yes, we're talking about the Nobel Prize in Chemistry. It was awarded yesterday to, yes, Martin Karplus at Harvard University, Michael Levitt at Stanford, and Aryeh Washell at the University of Southern California. Now, these are three computational chemists. So that made me very excited because these are my people. I'm a computational chemist as well. So I thought, great, this is a perfect opportunity to talk to you guys a little bit about what computational chemistry is and to explain that sort of thing and tell you a little bit about what I do. Now, the original plan was to get this out to the public. Okay, so just average Joe off the street could come in and say, oh yeah, I heard about the Nobel Prize in Chemistry. I'd like to see what this is all about. You guys all have a little bit of a clue about what's going on with chemistry, so this might be a little low level, but it'll be good. It'll kind of give a general overview of things. Okay, so officially, the official citation for the award is these guys got it for the development of multi-scale models for complex chemical systems. Okay. Now, there's a whole lot out there about this, because it's a huge news story. So there's all sorts of things in the popular press. New York Times science section has articles on this, and Reuters and NPR has done stuff on this. And the actual official Nobel Prize website, that's the official citation for why these guys got the prize. So you can go there, you can check that out, you can read that. If you haven't already read that, I suggest go and do that. It's interesting stuff. What I want to do today is sort of along the same lines, kind of do a general overview of why they got the prize and kind of talk a little bit more, maybe go a little bit more in depth into some of the things, hopefully explain some of the things that may have been a little confusing in these descriptions and answer any questions you might have about what you read. And then also talk about how that really relates to my research and things that are going on right here at Marist College. So, okay, first things first. talk about computational chemistry. Okay, so the first real question is, chemistry is an experimental science, right? It's the study of matter. Okay, so how do you study this? Well, you go into the laboratory, you take matter and you put it together and you see what happens. You see how it interacts. You observe and you write down your observations and you collect data and then you figure it out. Okay? So how can they give the Nobel Prize to people that don't do any experiments in this experimental science? Okay, that's the question. These are guys who didn't actually do experiments. They just kind of theorized about what should happen. And they used the computer to verify their theories. I mean, physics is the real theoretical discipline, right? The people that won the Nobel Prize in physics, Higgs and Engler, they got this for the theoretical prediction of the Higgs boson, and that's a great thing. It happened last year. Wonderful. But that's theory, theoretical physics. Chemistry is an experimental science, right? Well, it turns out that thanks in a large part to those theoretical physicists of a while ago, we have mathematical equations that model how matter interacts. Okay? And we can put those mathematical equations into a computer. Computers are great at solving mathematical or solving math problems, over and over and over again. Taking these routine math problems and solving it really quickly. And yeah, the computers are really good at that. So we can use computers to model how matter interacts. Okay, great. Well, no problem. Problem is that this problem can only be solved exactly for systems with one electron. Okay? So we're talking about hydrogen. That's it. While hydrogen is indeed very interesting, there's a lot more to chemistry than just hydrogen. So instead, what we have to do is we have to figure out some way to make some approximations somewhere along the way. Okay? So that's really kind of the business of computational chemistry. We want to figure out what kinds of approximations can we make in order to get the calculation to run. Okay, so we don't want it to take forever, but we want it to be able to give us enough information to solve the problem at hand. So that's really kind of what computational chemistry is all about. So there's really two ways of doing this. Okay, traditionally two main ways of doing this. One way is what are called ab initio methods. Okay, ab initio methods are based on quantum mechanics. Okay? So you're getting in there, solving the quantum mechanics, trying to use the fewest approximations possible. Okay? These methods are very accurate, or they can be very accurate, but at the same time, they're pretty slow. Okay? So yeah, you can get in there and solve these problems pretty exactly, but it's at a cost. Okay? The problem is, you can only solve the problem exactly for systems with one electron. Well, as soon as you get more electrons, the problem gets exponentially more difficult. And by more difficult, I mean it takes a lot more time. So back in the day when these methods were first really being developed, in kind of the early 70s, people would do calculations on a molecule with 3 atoms in it. And that would be done on a computer that was about as big as this stage area right here. And it would take a couple days on this triatomic molecule, and you wouldn't get really good answers. It's kind of slow going. Things are better now. I mean, computers have gotten a lot faster, a lot smaller. The software has gotten a lot more efficient. Okay, when I first started doing this stuff, the software that I was working on was described as 1 million lines of really bad Fortran. These are chemists, okay? These are chemists who are doing this stuff. They have a problem, they want to solve it. There's a computer, okay, just throw a bunch of code at it, try and figure it out. It was horrible code, it was inefficient, it was hacked together, but it worked, kind of. As things develop more, you get people who actually know what they're doing, and some computer scientists get in there and you get a little more efficient code. In this business, speed is everything, okay? Trying to do things as fast as possible. Why? Well, not because we're impatient, but because the faster you can do the calculation, the bigger the molecule. So that's the idea. You want to do these things really fast, but you still need a good bit of accuracy. Okay? The other problem here is these ab initio methods, you're looking at a static molecule. That's it, the molecule by itself. Okay? Now, molecules generally aren't hanging out by themselves. There are other molecules around, and those molecules interact. So, for example, the molecules in your body, okay? Well, those are, they're in water. You're basically a big bag of water, right? So these giant biomolecules that are in there are in water. So in order to treat this correctly, with quantum mechanical treatment, you have to really consider each one of those water molecules and how they interact with this big biomolecule. Okay? So that's a really, really hard problem. Okay? In addition, I should have said this before. So with these advances in computer science and better methods and faster computers, nowadays we can calculate things reasonably well, about 50 to 100 atoms, okay, which is a lot more interesting than hydrogen, a lot more interesting than a triatomic molecule, but still is a far cry from the big biomolecules in your body. Okay, we're talking on the order of 1,000 atom molecules. 1,000 plus atoms in those big molecules. So there's a lot of stuff that we can't do with these methods. Okay? In addition, right, you're considering this molecule to be isolated at 0 degrees Kelvin. Okay? Absolute zero. So most molecules aren't at absolute zero. In your body, right, 98.6 degrees Fahrenheit. Great. What does that mean for the molecule? Well, there's some residual energy around. So these molecules are moving around, they're rotating, they're vibrating. They're doing stuff. In order to get the problem right, you have to consider all of those different conformations. Huge, huge problem. Can't be done with these methods. Okay? The other way to do this is what's known as molecular mechanics methods. Now, molecular mechanics methods are based on classical mechanics. Okay, basically what you're doing is each one of your atoms is a hard sphere, a charged hard sphere. And all of your bonds are springs. So it's just ball and spring. Okay, this is the basic physics you learn in your freshman physics class. It's very, very fast because you don't have any electrons. Remember the problem up here? The problem with too many electrons. And down here, you don't have any electrons. So they're very, very fast. But that's a problem. Okay? Because if you want to study anything where electrons are changing, such as chemical reactivity, bonds are made, bonds are broken, electrons shift. You can't do it with these molecular mechanics methods. It just doesn't quite work out. So the Nobel Prize in Chemistry this year was really for bridging these two worlds. Okay? Bridging the very, very accurate but slow world of quantum mechanics and ab initio methods and this very, very fast world of classical mechanics, molecular mechanics methods. Okay? These are what are known as these multi-scale models we talked about earlier. Okay? So let's say we have some kind of molecule like this. So you've got this big protein sort of thing here, and this is in water solvent around here. Okay? But let's say there's some kind of a reaction going on here. Well, that reaction most likely takes place only at one very small active site. Here's where bonds are broken and formed right there. The rest of this is just part of the background, if you will. So the only place where you really need to do the very, very accurate quantum mechanical treatment is right in there at that active site. Okay? That's where bonds are broken and bonds are formed. That's where electrons are shifting around. So we really want to do our quantum mechanics right in there. But for the rest of this stuff, which isn't so important, we could do some easier method like these molecular mechanics methods. Now, out in here, out in the solvent, well, that's another matter entirely. What we're going to do with that, we can just treat that as a continuous field. And just treat that as a constant electric field. And this big enzyme here is kind of in a cavity inside that field, and that's, we can be done with it. Okay, great. Well, that sounds simple enough, but the problem is that these different regions interact with each other. Okay? The solvent is interacting with this molecular mechanics layer. This molecular mechanics layer is actually bound to that active site, so it's definitely interacting there. Okay? What these guys did, what Warshall and Levitt and Karplus did, was really kind of figure out how to approximate these interactions between these different regions. Okay? Thus allowing for the possibility to do calculations on things that are this large while still getting enough information on the one little active site that you really need. Okay. So that's really the bulk of it. That's really the main thrust of what they did. So, okay, one of the things that this allows you to do is really get a much more real picture of chemical reactivity. Okay? As chemists, when we think about chemical reactivity, we think in terms of these energetic landscapes. Okay? What I have here in this picture, okay, which I stole from one of these websites, basically looking at going up in energy right here, and then this axis here, and this axis here. These are different molecular parameters. You can think of this, maybe this is like a bond length over here, and this is a bond angle. So you're changing a particular bond length there, you're changing a particular bond angle, and looking at how the energy changes as we do that. Okay. So, you can think of this in terms of, just like a geographical landscape. Think about this as, some mountains and valleys and troughs and spines and all kinds of things like that. Okay? So, if you're, used to hiking, then this should kind of be a familiar sort of picture. Molecules tend to go to the lowest energy spot. Okay, so we're interested in what's going on here in these little troughs, these little valleys, little holes down there, so say there and there. And in a chemical reaction, right, you're going to go from one hole, one little valley there, one trough, up over a barrier, which we call the transition state, down into another valley down in here. Okay. Well, great. Well, with these ab initio methods, what you can do is you can calculate, if you have a small enough system, you can calculate, a stationary point right in here. You can calculate a stationary point in this trough right in here. Okay, and you can actually get a point right on top of that transition state right up there. Okay. A little more difficult to get transition states, but you can do it. It's doable. And when we do that, then we have our reactant energy, we have our transition state energy, we have our product energy. We get a very crude picture of the surface. Okay? But there's a lot more going on here. Okay? You don't just have one molecule, you have a lot of molecules. Okay? And these molecules are at some residual temperature. Think about, these biomolecules, the temperature of your body. So they're moving around, they're shaking. Okay? So what might happen is, instead of taking the lowest energy path from one hole down here, up over the transition state, to the other hole over here, instead, molecules might be kind of bouncing around here. They might kind of go up and then come down. Another one might go up here, come down. Maybe it goes up here, hangs around for a little bit, maybe goes down there, comes back. Another molecule may kind of go over here, but whoop, doesn't want to go back, so it comes back. And then, maybe one of them actually does kind of bounce around a little bit, but then it does go down. In order to get this right, what we have to do is consider all of those possible pathways. Okay? So what we have to do is take some length of time, consider a bunch of different, what we call trajectories, and see what happens on these trajectories over some unit length of time, see if they actually go to the products, if they actually come back to reactants, if they go somewhere else. Okay? So you have to do a whole bunch of these trajectories and then take some kind of statistical averaging of the whole thing and put it together. That's a much more accurate picture of what's really going on here. This is a huge problem. Okay? Not something you can do with ab initio methods. Okay? You can maybe do that for a very, very small, some very, very small molecules. You can run a bunch of trajectories, and that's fine, just looking at those small molecules. But if you want to look at a big enzyme, okay, you want to look at a big enzyme in solvent, then, yeah, you need these multi-scale methods. Okay? The quantum mechanical part looks at the actual bond breaking and making. The rest of it is the enzyme. The molecular mechanics treats that enzyme, does it very quickly. So we can do a lot of these trajectories. We can get a statistical average. We can get an idea of the real reactivity, a real picture of that reaction. Okay, great. All right, so here's a cool picture. Kind of clarifies this a little bit. So let's say we've got some kind of a big enzyme right here. We've got this big trough right in here. And some other molecule kind of sits in that trough right in there. And then we have a hydrogen transfer going on. Now, hopefully you can kind of see this. Do this quickly just for this one slide. So what we're interested in here really is a hydrogen transfer. This hydrogen right here transfers from this oxygen, boop, over to that oxygen. That's what we're interested in. Okay, so what we could do here is say, okay, well, let's just treat this little part of it, which is this part right in here. Okay? We'll treat this part of it with some kind of quantum mechanical method, because we have an atom shifting. Electrons are changing in here. We need to treat that with quantum mechanics, hit that with some high level. Okay? And then the rest of this backbone here, well, that's maybe pretty important. So, let's treat this with some kind of quantum mechanical method, but let's maybe do something that's a little bit easier. Okay, something that's not quite as rigorous. Make a few more approximations. Okay, so we can do that, and then the rest of this big enzyme out here, right? We can just kind of treat that with our classical mechanics methods, our molecular mechanics. Okay, we can divide this up into as many regions as we want using these multi-scale methods. Okay, these multi-scale methods will, take into account the interactions on the borders here and on the borders here, and out here, right? Here's our solvent. Okay, so basically putting this whole thing inside some big cavity and considering the solvent as a constant field. Okay. Not possible just looking at this whole thing with ab initio methods. Okay? So we take this whole thing, set it up, send it on a trajectory. Okay, give it some temperature, tell it what the temperature is. It's going to shake around, it's going to move. Some of the time that hydrogen might go over here, some of the time it might stay. We take a statistical average of the times. We take a statistical average of all those different trajectories, we get an idea of the reaction rate. Okay, that's the general idea. All right. At this point, I want to talk a little bit about one of these guys in particular. I want to talk a little bit more in depth about Aria Warsham for a bunch of reasons. By a not so major change of events in my life, okay, I could have ended up working for him. And it's not so far out there. I mean, there was a real possibility of working for him. I almost ended up. I could have ended up working for him. Okay, and it's not a far stretch to say that. Okay, I had just finished up at University of Georgia. I learned about a lot of these computational methods, a lot of the ab initio methods, and I was off in Israel at the Hebrew University doing that postdoc, doing some valence bond calculations over there. And it was just about finishing up at this point in time. And there was a grad student in the group, Avital Shirky. She was finishing up at about the same time that I was. Okay, so we were both looking to figure out what to do next. Okay. This is around the time, it's like late 90s. This is when biotech was booming. Okay, biomolecules were being really, really big. Biochem was huge. And all these biotech firms were popping up all over the place. Everyone was biochem. It was huge. Okay? So Avital, she, her ultimate goal was to get a faculty position back in Israel. That's what she really, really wanted to do. She thought, well, okay, if I'm going to be more marketable, I need to know how to do calculations on these biomolecules. Okay, great. Me, on the other hand, I wasn't so interested in biology. I never really loved it. I really wanted to end up in a place like this. I wanted to teach. I still wanted to do research, but I wanted to teach a lot of small college, a lot like Marist. So I wanted to go somewhere where I was going to get a little more teaching experience. So we went to our advisor and we said, okay, here's what we want to do. And he said, okay, Avital, you need to go work with this guy I know, Aria Warsham, okay? He's at the University of Southern California. He does these great calculations on biomolecules. It's similar to what we're doing. You need to go work with him. So Johnny, you want to teach? You go off to the University of Washington. They have this split teaching research program there. Get teaching experience. Great. Had things been slightly different, okay, had I expressed more of an interest in biomolecules and Avital, been interested in teaching or some other area, then things could have been different. I could have been working with Warsham. As it turns out, though, it would have been kind of cool to have a Nobel laureate on your resume, but things worked out for the best. She is right now has a faculty position at Hebrew U, and she loves her work there, and that's great. And job here. This is where I always wanted to be. I love my job here, and it's great. So things worked out for the best in the end. All right. The other thing about Marshall that I want to talk about, he's really known for doing these enzyme reactions, really looking at these enzyme reactions. And the way that he does it is with this method called the empirical valence bond method, or EVB. I shouldn't say the way that he does it, because he does a lot of different things. But one of the methods that he developed was this EVB method. Okay. Now, that's similar to what I do here at Marist. Okay, I do ab initio valence bond calculations. Okay, I'm just kind of doing VB without the E. Okay? So there's definitely a similarity there between what this Nobel laureate's doing and what I'm doing. So I want to talk about that stuff a little bit. But before I talk about this EVB method, I have to talk about just valence bond methods in general. Just kind of do a little bit of an overview about this. Those of you who've seen me talk before have probably seen this before. But that's okay. It's a slightly different approach here. Okay. So let's say we have some kind of a molecule, such as this. Okay, here we're interested in this molecule. Okay, great. Ethane right here, standard small molecule. But let's say we're really just interested in this bond right here, the CC bond. Okay? So we just want to look at that one bond. Let's say we want to get bond energies or something like that. Okay, well, in the valence bond treatment, what we can do is we can, take one electron on one side and one electron on the other, spin pair those together, and there's our 2-electron bond. Simple enough. Okay? In order to get a better picture of things, we need to consider the possibility that both electrons are on either one side or over on the other. And then overall, to get the overall energy of this thing, we have to consider all three of these structures at the same time, take a weighted average of these three things, and that gives us our total energy. There it is. Basic idea of valence bond theory. Now, this is really the way that we are all trained to think. As chemists, this is familiar to us. This is the way we're taught. In general chemistry classes, we draw Lewis structures like this. Okay? We go through organic and we talk about hybridization. Hybridization is a direct result of this type of looking at individual bonds. Okay? We talk about bond energies. We talk about functional groups being bound to each other. We talk about bonds breaking, bonds forming. Okay? We talk about bonds. As chemists, we like bonds. This is how we're trained to think. We think about molecules in terms of buildup of individual bonds. A bunch of bonds together to make your molecule. Okay. So that's the way that we think. However, the way that these computations are done is not with valence bond theory. Sometimes they are, but the more popular method is what's based on molecular orbital theory. Okay? Molecular orbital theory looks at the entire molecule. A little bit different. Okay? Why is that? If VB is the way chemists think, why do people do it with MO theory? Well, VB, valence bond theory, is actually these days is kind of seen as sort of an inferior theory. It's seen as flawed. As, this is an incorrect theory, so we don't want to do calculations with that. We want to use the correct theory, which is MO theory. Well, it wasn't always that way. Okay? Back when the theoretical physicists were first, figuring out all this quantum mechanical stuff, okay, the chemists didn't like it. It didn't really jive well with chemists. It doesn't really work. Okay? They're looking at the molecule as a whole. They're looking at these big whole molecules. And chemists, think in terms of bonds. So chemists didn't like it. Okay? Until Linus Pauling came around and really developed valence bond theory. Basically what he did is he took the language of quantum mechanics, or he took this new theory in physics, this new quantum mechanics theory, and he put it into a language that chemists could relate to. He put it into a language of bonds. Instead of looking at the whole molecule, he decided to formulate this in terms of individual bonds. And then in order to get the properties of the whole molecule, put the individual bonds together. Okay. And that worked really well. Okay, chemists really loved it, and valence bond theory was really, really big back in the day. Okay? But then, the tide started to turn a little bit, probably kind of towards the 50s and the 60s. Things started to shift more towards MO theory. Okay? Well, what happened at this point? Well, at this point, computers started to kind of come on the scene, and as it turns out, MO theory is a lot easier to calculate than VB theory. And in addition, there were a few of these, catastrophic failures of VB. Okay, something as simple as the O2 molecule. VB gets it wrong. Okay, so people thought, well, for something that simple, if VB gets something that simple wrong, it must be a flawed theory. Let's just throw it out and just look at MO theory. Okay. As it turns out, all these, catastrophic failures of VB were really just misapplications. That's a topic for another talk entirely, so I'm not going to get into that so much, but just leave it at that. Okay, valence bond theory is not a flawed theory, but it never really recovered from that major blow. So it's kind of been making a resurgence recently, but it's still not as popular as those MO methods. But there's a lot of really slick things you can do with VB. Okay? For example, let's take a look at a standard textbook organic reaction. Okay? Something like this. So we've got a hydrocarbon up here. Okay, it's bound to this leaving group. You got a nucleophile that comes in. So you go through this transition state where you're making the carbon nucleophile bond there, and you're breaking that carbon leaving group bond, and then you get your products where the carbon is bound to the nucleophile, and the leaving group is off. Textbook organic reaction. Okay. The way we can look at this with VB theory is we can get we can look at a reactant VB structure. It looks like this, where we have our carbon bound to that leaving group. And then the nucleophile is just kind of off in the distance over here. Great. We can also create to think of this as a product valence bond. Here we have the nucleophile bound to the carbon. And the leaving group is off here, not bound to the carbon. Now, this product VB wave function up here, this product VB structure, is going to be a lot higher in energy because we have this long carbon nucleophile distance there, so you're not really going to get much bonding. So that's very high in energy, whereas this structure where the leaving group and the carbon are bound together, that's a lot lower in energy because you have an actual bond that's close together. Okay. Think about what's happening in the course of the reaction. Okay? This reactant structure is going to go up in energy. Why? Because the leaving group is coming off. It's getting further and further away from that carbon. So we have this kind of long carbon leaving group bond. It's not much of a bond, so this structure is a lot higher in energy. Meanwhile, the product VB structure is going to go down in energy. Why? Because that nucleophile is getting in close to the carbon. We get that carbon nucleophile bond at a nice short equilibrium bond distance. And there we have it. Okay? The overall reaction is just a superposition of these two states. So we combine those two things together, we get our reaction profile. Going from reactants to products over the transition state. There it is. Nice, clean, concise picture of chemical reactivity. Now this is kind of what's going on with the EVB method. Okay? But instead of, looking at a small structure like this, instead of H's up here, you've got some, gigantic enzyme sort of thing coming off here. But we have our active site where the bond is being formed and the bond is being broken. So what the EVB method does is it looks at some sort of reactant VB structure, looks a little bit like this, treats that quantum mechanically. Okay? Now the rest of this stuff, instead of hydrogens here, remember we've got a big enzyme coming off here. The rest of that is treated as, with molecular mechanics. And we use these multi-scale models to, model the interaction between the classical or the molecular mechanics part and the quantum mechanics part. Okay. And then in addition to that reactant VB structure, we have this product VB structure. Same thing. We're just treating this part right here with ab initio methods, and then the rest of it is treated with the molecular mechanics methods, the multi-scale methods, and then combine the two. Now the E part in the EVB, the E stands for empirical. That has to do with how you combine these two structures together, these two different VB structures. Okay? And that is done by taking some empirical parameters. You can take either some experimental parameters if they're available, or by doing another calculation on the surface prior to doing this EVB approach. Okay, so that's the idea. Very similar to the types of stuff that I do. And in fact, recently I've been really thinking a lot, the past couple of years I've been thinking a lot about how to do this sort of thing. Okay, how to do the same sort of approach. Really kind of getting rid of the E part, getting rid of any empirical parameters, and doing this on some kind of a large scale. Not quite enzyme large scale, but figuring out ways to do this on a larger scale than we can currently do this with ab initio PV methods. Okay? Now I've been just kind of thinking about this a lot in recent years, just really started working on this earnestly with Andrew. Andrew James is helping me out with this. That's kind of his senior project, kind of looking at possible ways of doing this. We have some ideas, but nothing concrete as of yet. Okay. So in order to sum things up here, kind of conclude, a couple of things to say. I want to go back to the original question that we had. Okay? How can you give the Nobel Prize in chemistry, which is an experimental science, how can this be given to people that don't do experiments? How is that possible? Well, calculations of the new experiments. Okay? Now I have this in quotes right here because this, this is something that I got off of a video, like a YouTube video that I got on the Nobel website. This is basically something that the director of the committee that chose the Nobel Prize was being interviewed, and this is something he said. Okay? Calculations are the new experiments. Okay? Now, back when things were first developing, back in the early days of computational chemistry, back in the days when all these Nobel Prize winners were really trying to do these calculations on enzymes and stuff, it's kind of absurd. Back then, theory was kind of seen as, it's kind of like a hobby. Okay, so theorists would, work really hard. They had their gigantic computers that would, calculate the triatomic or something, and get these results, and they'd say, hey, look what I got. And the experimentalists would say, that's cute. But look what I did, okay? I did some real chemistry. I took a real molecule, and I did this real experiment with it, and I got some real results. Okay? And those results don't agree with your theory, so your theory's wrong. So go away. Okay? Nowadays, the tables are kind of turned. So you're just as likely to have a situation where theory says one thing, experiment says something totally different, and the experimentalists say, uh-oh, I wonder if my experiment's screwed up. I better go back and check things. I better go back and look at my numbers. I better go back and see if I did everything right. It's kind of come full circle, totally the other way. The computer is now just another tool in the chemist's arsenal. Okay? You want to figure out a problem, well, you can do experiments, you can do spectroscopy, do all kinds of things. You can use the computer. Any means necessary to figure out the problem. Okay? So what happens a lot of times today is people will say, okay, I want to figure this out, I want to make this molecule, well, let's model it on the computer first. And that will then give an idea of how to tailor the experiments to get to the final results. The other way things often work is experimentalists will do stuff and they'll get some results and they'll say, I have no idea what this means. So let's put it through the let's put it through the computer to interpret the results. So they kind of go hand in hand these days. And the reason for that is really thanks to people like Ari Warshel and Martin Karplus and Michael Levin, for making these theoretical methods something that is possible to do. And with these guys, especially for the big biomolecules. Now I should mention this, I didn't say this before, those ab initio methods, yeah, there was a Nobel Prize awarded for that back in 1998 to John Popel and Walter Cohn for doing the same kind of thing, making those ab initio methods viable as well. Okay, another point I want to make here is this. Again, another quote. Valence bond, rebirth of the phoenix or relic from the Stone Age. Okay? This is the title of a paper in Theoretical Chemistry Council 2006 by Avital Shruki. Avital, as you'll remember, right? She was that graduate student who was at university or at Hebrew University, same time I was, and she went off to work with Ari Warshel, and this is something she published after that. She was back in Israel, and yeah, it's a discussion of where VB is or was at the time in 2006. Okay, is it coming back? Is this the rebirth, or is it just something that's just going to die off? Okay. Well, now that Warshel won the Nobel Prize for doing or part of what he did was develop this method that is based on valence bond theory. Okay? This could usher in a golden era of VB. This could be a turning point for valence bond theory. It could come front and center, and that would be awesome for me because I've been doing this for a long time. This would be great for my research, great for Marist, because this is kind of, I'm one of the few people in the world that does this. We're kind of a small community for a small handful of people. So that would be pretty cool. So we'll see. What's going to happen? Really only time will tell. Okay, so that's about it. Okay, so I'd like to also thank all of you guys for coming out tonight on such short notice. We wanted to get this out as soon as possible, so hopefully I've kind of cleared up a few things about computation chemistry and why these guys got the prize. If you have any questions, I would be happy to try to answer those. Thank you. Yeah.
When was this work actually published?
Which one?
Whatever they.
Oh, that's a good question. So when was this actually published? Between yesterday and 1965. It's really kind of a lifetime achievement sort of thing. There's no one real like, boom, they did this. There are a few big milestones. I mean, like I think Levitt and Warshall did the first real calculation of a protein folding. Not sure exactly when that was. That might have been 1968. Maybe that was 72, I'm not sure. But yeah, there's no real one thing. It's kind of over many years doing this stuff. Another thing to say along those lines is there are many other people that didn't get this award. Okay, this award, it's kind of a lifetime achievement for these guys because they're kind of big guys in the field, but it's more also an award to the field itself, the field in general, just for coming from where it was to where it is now. Remember back in the day in grad school, we would kind of make jokes about doing calculations on DNA. Yeah, see you next year. That's as long as it would take you that long. That's the idea. But now it's totally possible. Yeah, so it wasn't any one particular thing. It's kind of career. Okay. What else? That's fine.
So now I was kind of answering the protein folding. Are there particular examples of where imaging is very different? What are the implications? Does it allow people?
Yeah, protein folding is the big. Yeah, that was the real big thing. It allows, you can look at that. So protein folding, for one, proteins are big, so you can't just calculate them stationary anyway. You need these force field or these multi-scale models to calculate just one structure. But then to do a reaction where the thing's actually moving around, and those molecular dynamics which these guys also developed, helped develop. Yeah, that takes a lot as well. So the protein folding is a huge thing here. Drug design is a pretty big thing too. I mean, that's big for pharmaceuticals these days. And so, yeah, you can't really do that so much with the ab initio methods, so because they're big. These drugs are big and affecting these big enzymes. So yeah, biomolecules, really, the ability to do chemistry on molecules of the size of biomolecules. In addition, another area where these things are being used, just materials development. Like solar cells and semiconductors, things like that. You're doing all these materials. Well, how do you calculate those things? They're big. Even these little tiny, semiconductors, little tiny computer chips are still big, chemistry-wise. So how do you do calculations on these? How do you kind of figure out before going into the lab and before wasting a lot of time and money doing experiments on things that may or may not work? Okay, you can go to the computer first and let the computer figure out some possible targets, and then you can go to the laboratory and start to mix up those targets and have a better shot at getting something that actually works. Yeah, right.
I noticed in that one picture towards the beginning with the multi-scale models, there's something about a dielectric medium. I was wondering what that was.
Yeah. So basically this.
Yeah.
Yeah, so we're talking about dielectric medium. Okay, so that's basically, your solvent out here, instead of considering each individual water molecule in this case, because you got, billions and billions of those things out here, which would be a mess, you can't calculate that. So instead, you're just calculating this whole thing as basically a big force field. Okay, and that's what's kind of referred to as this dielectric medium. Each solvent has what's called its dielectric constant. Okay, which is basically kind of, it gives you an indication of how charge is transferred through that medium. Basically a quick, dirty way of explaining it. So you can calculate this whole thing in the presence of this constant medium here. You're kind of considering this being a cavity in this, charge and kind of this constant interaction between this whole thing and this molecule here.
You said before that the big bottleneck is the number of atoms you have in a whole molecule. Does it also matter what atoms are? Like such as what you mentioned before with semiconductors, does it matter that you have F and G orbitals around there? Does adding more electrons to the equation really change things up a lot?
Yes, and actually it's really the electrons that really matter. Okay, the electrons are, so yeah. So like a lot of these things have hydrogens. Hydrogens don't matter so much. Of course they matter, but you've got a proton and an electron. It's not such a big deal. I mean, a hydrogen is a lot easier to calculate than say an iron atom. You've got a lot more electrons in there. It's really the electrons that are the problem, because that's really why we can't solve these exactly. It's that interaction between electrons that you can't calculate, because of Heisenberg's uncertainty principle, you don't know where the electrons are, so you can't calculate that interaction. So yeah, it's really the electrons. So the more atoms you have, the more electrons you generally have. But if you have heavy atoms, then you have more electrons.
So are the companies making money out of this bill? We talk about drug design, other companies are making programs based on this.
Oh yeah, it's big money. You mean the actual software, or the companies that are using the software?
Yeah, I wonder if, there are companies that now it's calculations possible with packaging. My software and some pharmaceutical companies.
Yeah, oh yeah. Actually, Gaussian, which doesn't really do this yet. But just as an example, Gaussian, we have that here. It costs us like $5,000 or something like that. They sell it to industry for like $20,000. The industrial price is much, much higher. And there are definitely programs out here that do this sort of thing, commercial programs, like, geez, I don't know what the electromechanics ones are. I'm not even sure what the electromechanics ones are. Amber, I think, is one, and Charm's the other big one. These things, yeah, they're people are making some big money selling these things.
Doesn't QChem do some of the QLM?
It does to some extent, yeah. There are a bunch of other packages that have this. Actually, it's kind of true. Yeah. On a much smaller scale, Gaussian will do the QMMM stuff. That's true. Yeah. And actually, most of the packages have that stuff in there. These onion methods, which are along the same lines. And QChem does it, Gaussian does it. Actually, games might do it too. Doesn't it? Does.
It does. I know it does. I know about things about that stuff.
Yeah, so it's becoming much more prevalent. It's in all the standard commercial packages.
So could it like an area of the future?
Yeah, well, it's been a big area. It's been drug design. It's been a big thing. People that come out of, a bunch of people I went to grad school with are now, working for drug companies. They're doing this sort of thing. They're designing these molecules, using these programs, making the big bucks. But yeah, maybe it will be even bigger now than this happened.
But I don't think people think of computational methods when they think about careers in chemistry. This doesn't come to mind.
Should. Yes.
Yeah, I don't know how many of you were there last year, but actually the guy who gave the keynote speech at the undergraduate research symposium, he was a molecular modeler that made a lot of money selling his company. He was in pharmaceuticals, and he sold his company to some larger company and made a lot of money.
But that was, yeah, that was just straight up molecular mechanics.
Yeah, that was in the side stuff.
This is, yeah.
I mean,
And that's, what you can do a lot of stuff with molecular mechanics, what they were doing, you know, you don't have electrons there, but you can look at these giant molecules and they're really good at getting structure. And you're going to see how these things will bend and give you the structure, but you actually want to find out what's going on with the reaction, then you're kind of in trouble. But you can get the overall structure, you can see where, oh, there's a cavity right there, this drug might fit in there, and then this drug might fit in there, and do all these docking kinds of things that are pretty neat. But actual reactions where electrons are transferred back and forth, you can't do those.
Any other questions? Okay. Join me in thanking Morrison Galbraith. Again, thanks for coming.
After this was on the ACS newsletter.
Because we decided to.
Yeah. We sent it out to the issues.
You're really pushing out that beer talk. Science of beer. Where are you going after? Science of beer. Oh yeah, I did. Oh yeah, it was yesterday. I opened it. I read it. I read it too.
I wish I read it afterwards. Yeah, it helps.
They'll be fluid.
Yeah. Not gonna lie, I looked at the tweets more.
Yeah, in a couple of days we'll be looking.
Yeah.
Even sent it to Poughkeepsie Journal.
I retweeted that.
Yeah,
Well, we're thinking, you know, sometimes the story.
That was like a general overview. Yeah. Well, as you were doing it, I was pulling up my own pictures.
I like still figures.
But they don't have the bio of them like they did on mine, so that's why I read
Oh, okay.
the one on mine.
Yeah, I read through that last night.
You know, that protein one was lysozyme.
Cool.
Should we know that by now? I'm not sure.
I gotta go with the pack. There you go, Kim.
You're on camping?
Pack all my warm stuff.
Oh, what time are you leaving?
I don't know. Be nice to get out as early as possible.
Well, because I was actually in Buffalo for the weekend, but it's my friend's birthday. So I just wanted to still have these short.
Yeah, we should get together for a little bit. We finished at 11, so we can meet then and quick go over a few things.
What? Oh, yeah, you told me. I kept checking it while I was in biochem lab.
It looked horrible until I changed the title.
What was wrong with it?
Like a flat line.
Oh. Oh.
Wasn't much of a calibration.
Hey, do we need to do anything with that?
Just recording us now.
on? Imagine it wasn't
I
recording.
think that guy turned it on before he left.
You have a 10 cam?
Yeah, hold on, it's still recording.
We got